Question 1, the Venn diagram, where P and Q are probabilities, shows the three events A, B, and C, and their associated probabilities. Part A, find the probability of A. So the probability of A is anything in the A circle. So 0.13 plus 0.25. So that is 0.38. The events B and C are independent. If they're independent, that means the probability of B times the probability of C is equal to the intersection, the probability of B and C. So find the value of P and the value of Q. So let's use that. The probability of B times the probability of C equals the probability of B and C. So the probability of B is all the ones in B added together. That's 0.6 times the probability of C, which I'm just going to write as probability of C for now, equals the intersection, which is 0.3. And that means the probability of, so divide both sides by 0.6. The probability of C is a half. And so P is half, take away 0.3, which is 0.2. So we know P is 0.2. The whole thing has to add up to a whole. So we add up what we've got here. So 0.13, 0.25, 0.05, 0.3, and 0.2. That adds up to 0.93. So 1 minus 0.93 is 0.07. So that is Q. Q is 0.07. Find the probability, part C, of A given not B. So A given it's not in B. So what's the probability of it not being in B? It's the ones not in B, so not in the B circle. Everything not in the B circle, so 0.13, 0.2, and Q. So the probability of not B is 0.13, 0.2, and 0.07, which is 0.4. And the probability of A given it's not B, so out of the ones that are not B, so we're not including this, out of the ones that are not B, what's the probability of getting A? It's 0.13. So 0.13 over 0.4. Is 0.325. Question 2. A machine fills packets with sweets, and 1/7 of the packets also contain a prize. The packets of sweets are placed in boxes before being delivered to shops. There are 40 packets of sweets in each box. The random variable t represents the number of packets of sweets that contain a prize in each box. State a condition needed for t to be modelled by a binomial expansion with n as 40 and the probability 1/7. So in order to be a binomial, we need the chance of picking a pack that contains a prize to be the same every time. Each one has to be independent of the one before it. And the probability has to stay constant. Has to always be 1/7. So I think we can just say, or we can just say, each event must be independent. Or even the chance of getting a prize each time must be independent. Each event must be independent. And I'll also write, and the probability must always be 1/7. Part B, using T is modelled binomially with n as 40 and p as 1/7. Find the probability the box has exactly 6 packets containing a prize. So we just grab the calculator, menu, go to distribution, and this is a binomial probability distribution with a variable. So x is 6, there are 40, and the probability is 1/7. So we get 0.173. The probability we have fewer than 3 containing a prize. So when we're using the binomial, we are using, it's always got to be less than or equal to. So we want the probability it's less than or equal to 2. So it's the probability T is less than or equal to 2. So binomial cumulative. So this time we're after 2, but it's still 40 and the same probability. We get 0.0616. Camille's sweet shop buys 5 boxes of these sweets. Find the probability that exactly 2 of these 5 boxes have fewer than 3 packets containing a prize. So we know the probability a box has got fewer than 3 packets containing a prize. That is our last answer. So this time we've got 5 chances and we want 2. So we want to change our binomial into x is distributed binomially with n as 5 this time. And the probability of success, 0.0616. So then the probability x equals 2, was it? Probability x equals 2. So back into the calculator. Binomial probability distribution. So x is 2. N is 5. And this is 0.0616. So 0.0314. Camille claims the proportion of packets containing a prize is less than 1/7. In a random sample of 110 packets, 9 packets contain a prize. use a suitable test to test Camille's claim. You should state your hypothesis clearly and use a 5% significance. Level of significance. So we have, so our null hypothesis is what we believe to be true. So not what Camille thinks, the original one. So that's the proportion. Probability is 1/7. So probability is equal to 1/7. That's our null hypothesis. Our alternative hypothesis is he thinks it's less than 1/7. So the alternative hypothesis is what the person thinks, what we're testing. So less than 1/7. So that's the hypothesis. Now we need to do the test. So in a random sample, so n is going to be 110 and 9 contain a prize. So what's the chance of that happening? What's the chance of 9 or less containing a prize? So we're going to do a binomial distribution with n as 110. Probability is 1/7, and we want the probability that we have 9 or less than or equal to 9. So let's see what we get. So we're going to go for a binomial cumulative. We want 9, we've got 110, and it's 1/7. 0.0383. 0.0383. So that's less than 5%. Less than 5%. So 0.0383 is less than 0.05. So this is going to happen less than 5% of the time. So we can say there is evidence. To support Camille's claim. Question 3. Ben is studying the daily total rainfall, X millimeters, in Leeming for 1987. He used all the data from a large data set and summarized the information in the following table. Explain how the data will need to be cleaned before Ben can start to calculate statistics such as the mean and standard deviation. So we have trace included in it, which is going to have to be changed into something. So trace is between 0 to 0.05. So we can change trace into 0, or we could change it into halfway here, 0.025. Either one of those will be okay for the answer. So TR should be changed into 0.025, and that is halfway between 0 and 0.05. So trace should be changed into 0.025, which is halfway between 0 and 0.05. Using all 184 of these values, Ben estimates that the sum of the x's is 390 and the sum of the x squareds is 4,336. We need to calculate estimates for the mean and the standard deviation. So the mean is add them all up and divide by how many. So sum of x over n. Mean is equal to the sum of the x's divided by n. So 390 over 184. .390 over 184 is 2.12. And the standard deviation? The standard deviation, we're going to have the square of the mean of the squares minus the square of the mean. That's the variance, so we're going to do the square root of the mean of the squares, which is 4336. 4336 over 184 minus our last answer, the mean squared. The mean of the squares minus the square of the mean. So the square root of 4336 over 184 minus our last answer squared, and that is 4.37. So that's the mean and the standard deviation. Ben suggests using the statistic calculated in part B(I), so the mean, to estimate the annual mean daily total rainfall in Leeming for 1987. Using your knowledge of the large data set, give a reason why these data would not be suitable. So it's not the whole year. We've only got this half a year, 184 days. And so we only have data. The large data set from May to October. So we only have May to October. May, June, July, August, September, October. Yeah, that's the 6 months. We only have data from May to October, so it won't be representative of the whole year. So not representative of all of the year. And the second part, state given a reason how you would expect the estimate in part BI to differ from the actual annual rainfall in Leeming in 1987. So would we expect the actual rainfall to be higher? So this is the summer that we've got data for. We don't have data for the winter. So we could say it would be the actual annual mean rainfall. The actual rainfall would be higher because it would rain more in the winter. The actual rainfall would be higher because it would rain more in the winter. Question 4. A study was made of adult men from region A of a country. It was found that their heights were normally distributed with a mean of 175.4 centimeters, standard deviation of 6.8 centimeters. Find the proportion of these men that are taller than 180. So we're just going to use the normal distribution. So let's go into menu, distribution, normal cumulative. So taller than 180. So the lowest is 180. The upper, let's just pick a huge number. Standard deviation is 6.8. And the mean is 175.4. So we get 0.249. So the probability, 0.249. A student claimed that the mean height of adult men from region B was different to the mean height from region A. A random sample of 52 men from region B had a mean height of 177.2. The student assumed the standard deviation was the same for both A and B. Using a suitable test, assess the student's claim, state your hypothesis clearly, use a 5% level of significance. So a student claimed the mean height was different. So not higher or lower, just different. So our null hypothesis is that it's the same. So the probability, the height even, is, or the mean, 175.4. So the mean is 175.4. The alternative hypothesis, what does the student say? It's different. So the mean is not 175.4. And then we've got a sample. So we're going to change our standard deviation for the sample. So our standard deviation is going to be 6.8 over the square root of the sample size over root 52. So we're going to have a normal distribution with a mean of 175.4 and a variance 6.8 squared over 52. So that's just, and we want the probability that it is bigger or equal to 177.2. So we want the probability that x is bigger or equal to 177.2. So we're just going to put it in the calculator and see what we get. So that is normal cumulative, our lower 177.2, our upper we'll keep as a million, our standard deviation is 6.8 over square root 52, and our mean 175.4. That's 0.0281. 0.0281, which, if we double, it's a two-tailed test, so it's just not 175.4. So we've got (2.5%) on each side if we split up our significance level. So 0.0281 is bigger than 0.025, bigger than 2.5%. So there's not enough evidence. So there's not enough evidence to support the student's claim. There's not enough evidence. to support the student's claim. And part C, find the p-value for this test in part B. So what is the probability of getting the result we got? Set 177.2. So the chance, this side we had 2.81%. So if we had the same on the other side, 2.81%, that means the chance is 2 times 2.81. So answer times 2, 0.0563. 0.0563. So 5.6%. Question 5. Tissam is playing a game. She uses a ball, a cup, and a spinner. The random variable x represents the number the spinner lands on when spun. So x is the number it lands on when it's spun. The probability distribution of x is given by the table, where A, B, C, and D are the probabilities. To play the game, the spinner is spun. Tissam then stands x centimeters from the cup and tries to throw the ball into the cup. The event S represents the event that Tissam successfully throws the ball into the cup. To model this game, Tissam assumes that the probability of S given X given is K over X, where K is a constant. The probability of getting S is K over X, where K is the same for all of the X's. So if we've got the probability of S, it's going to be K over 20, K over 50, K over 80, and K over 100. That's the probability of getting S every time. The probability of S and the probability of X is the same whatever value of X is obtained from the spinner. So we've got half the chance of getting it in if it's 100 as opposed to 50, but the probability of getting both of them should be the same. So the probability of D times K over 100 should be equal to the B times K over 50. So the chance of getting D should be double the chance of getting B. The chance of getting the D on the spinner should be double the chance of getting B, so that the chance of all of them is equal. Chance of getting it in all of them is equal. So you should have more attempts on the one that's further away. Okay, so using Tissam's model, show that C is 8/5 of B. So C is 8/5 of B. Yeah, so C should be bigger than B in order for the chance of getting it in to be the same. So we're going to use the probability of S and, so times the probability of the X is the same for all of them. That means it's equal. Probability of C times K over 80 so C times K over 80 should be equal to B times K over 50. So divide both sides by K. So that's 1/8 of C equals 1/5 of B. So simplifying them both, dividing both sides by or timesing both sides by 10 and dividing both sides by k. So to get c by itself, times by 8, 8/5 of b. Find the probability distribution of x. So we can do the same for the other ones. So a times k over 20 is equal to b times k over 50. So same again. So half of a equals 1/5 of b. And then b equals 5 over 2a. And then let's do the same for d. So k over 100. d times k over 100 is equal to b times k over 50. So 1/10 of d equals 1/5 of b. d equals 2b. And if I change this one into a equals 2/5 of b. So they're all in terms of b, and all the probabilities have to add up to one whole. So a plus b plus c plus d must equal 1. A is 2/5 of b. B is b. C is 8/5 of b. And d equals 2b. So we've got 2/5 and 8/5 is 2. 10/5, 2. So 2, so 3, 4, 5. 5b equals 1. b must be 1/5. d is 2b. So 2/5. C is 8/5 of b. Eight-fifths of 1/5, so 8/25. And A is 2/5 of b. 2/5 of 1/5, which is 2/25. So the probability distribution, we've got everything now. So 20, 50, 80, 100. And it was 2/5, 1/5, 8/5, and D was, that's not right, 2/25, 1/5, 8/5, 2/5. Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimeters. He successfully gets the ball in the cup 30% of the time. State given a reason why Tissim's model of the game is not suitable to describe Nav playing the game for all values of x. So 30% of the time he gets it in. So the chance of getting it in is S. So S is 30%. So that would make K 30. So K would be 30. Part C. So if K would be 30, it doesn't work because if K's 30, that's fine for the 100, but you can't have 30 over 20 for A for 20 when it's 20 centimeters away, because that's bigger than 1. So the chance of getting it in can't be more than 1. So K cannot be 30 or nav, but K cannot equal 30 for 20 centimeters for X equals 20, as the probability would be 30 over 20, which is greater than 1. We can't have a probability greater than 1. Question 6. A medical researcher is studying the number of hours T a patient stays in hospital following a particular operation. The histogram on the page opposite, on the next page, summarizes the results for a random sample of 90 patients. Use the histogram to estimate the probability T is between 10 and 30. Let's look between 10 and 30. So we want the area between 10 and 30. So what is this area? So we're going to do base times height. And it is, so between first part of a box. So we have 2 times 4.2. 2 times 4.2. We have, so 12 to 16, 4 times 4. 16 to 20, 4 times 3.5, and 20 to 30 is 10 times 1. So we have 2 times 4.2, 4 times 4, 3 times 4 times 3.5, and 10 times 1. That adds up to 48.4. So 48.4. The total area should be 90. So 48.4 over 90. 121 over 225, or 0.538. 0.538. For these 90 patients, the time spent in hospital following the operation had a mean of 14.9, standard deviation of 9.3. Thomas suggests T can be modelled by a normal distribution with a mean of 14.9 and a standard deviation of 9.3. With reference to the histogram, state, given a reason, whether or not Thomas's model would be suitable. So this isn't a normal distribution. It is not suitable. A normal distribution has to be symmetrical. It can't be skewed to one side. So the distribution is not symmetrical. And Zhang suggests the frequency polygon based on this histogram could be modeled by a curve with equation y equals kx times e to the power of negative x, with x 0 to 4, where x is in tens of hours, so it's 0 to 40 hours. X is in tens of hours and k is a constant. Use algebraic integration to show that the integral of x e power of negative x between 0 and n is equal to this. So we're integrating. We've got two things multiplied together. When we've got two things multiplied together in an integral, we look to integration by parts. So integration by parts says the integral of u dv dx with respect to x is equal to uv minus the integral of v du dx with respect to x. So we pick one of our parts to be u and one to be dv dx. We're going to have u as x because when we differentiate it, it goes to 1. So u is x and dv dx is e to the power of negative x. So u is x, dv dx is e to the power of negative x. That makes du dx 1. And it makes v the integral of e to the power of negative x. So when we integrate or differentiate e, it stays the same. But we're going to divide by the power differentiated, which is negative 1. So it's going to become negative e to the power of negative x. So now we can put this in to our integration by parts. So the integral of u dv dx, x e to the power of negative x, with respect to x, is uv negative x e to the power of negative x minus the integral of v du dx minus e to the power of minus x. We're then going to integrate minus e to the power of minus x, which is going to become e to the power of minus x. So it's just going to change the sign. So it's minus e to the power of minus x. Then we've got to put in our two limits, 0 and n. So between n and 0, between n and 0. So substituting n, substituting 0, and take them away. So minus n e to the power of minus n minus e to the power of minus n minus 0. That's going to be 0, the first one. Minus e to the power of minus, well, 0. Minus 0 is 0. And e to the power of 0 is 1. So that's minus minus 1 is plus 1. So minus n e minus n minus e to the power of minus n plus 1. We just need to make it look like the answer. So we're going to factorize out the e minus n. Factorize out e minus n. Let's factorize out minus e minus n. Minus e minus n. So that will leave n plus 1. And just write it the other way around. So 1 minus n plus 1 times e to the power of minus n. Show that for Zhang's model, k is 99 to the nearest integer. So n is 4. When n is 4, that should be all of the people, and it's 90. So the area underneath is 90 when n is 4. So when n is 4, and wait a minute, it's k times it, isn't it? So it's k times our answer. So when n is 4, k times our answer is 90. So part D was that. When n is 4, k times 1 minus n plus 1 e to the power of minus n equals 90. So k times 1 minus 4 plus 1 times e to the power of negative 4 is equal to 90. 1 minus 5 e to the power of negative 4 is 0.908. 0.908k is 90. Divide by 0.908, we get 99 to the nearest integer. Estimate P, the probability of the time being between 10 and 30 using Thomas's model, which is the normal distribution. So distribution, a normal cumulative between 10 and 30, standard deviation 9.3, mean 14.9, 0.649. So Thomas's model 0.649. And the same for the other model. So the probability between 10 and 30. So using Zhang's curve and the answer to part C. So that's between 0 and n. We want between 10 and 30. So it's going to be 3 and 0, take away 1 and 0. So we'll substitute in 3 for n and 1 for n and take them away. So substitute in 3, substitute in 1 and take them away. So it's 1 minus 3 plus 1 e to the power of minus 3. No, it's not. It's k times that, 99 times that. And it's 99, 1 minus 1 plus 1 e to the power of negative 1. So substitute in 3, substitute in 1 and take them away. So it's the area. So we've got our curve. Looks something like this. So the area up to 3 is all of this. And then we take away the area up to 1, which is this bit. So that just leaves between 1 and 3. So let's work them out. So 99 times 1 minus 4 e to the power of negative 3, 79.3. Store it as A. And then same, but with negative 1. So 1 plus 1 will be a 2. 26.2. Take them away. A takeaway answer, 53.1. 53.1. That's the area. So the probability, 53.1 over the total, which is 90. and that's 0.590. And finally, part F, the researcher decides to use Zhang's curve to model the probability, the times between A and B. State one limitation of Zhang's model. So it only works up to 40 hours. So the model would not work for a time greater than 40 hours.